So let's discuss on the example one. Okay, so basically we will discuss on the three example in this topic. Okay, so for the first examples we will analyze the arch with same level of support. Meanwhile, in the second examples we will analyze the arch with different level of support, and they have a combination of load which is a UDL and point load. Okay, and third examples we will draw the bending moment, shear force and axial diagram for the arch. Okay, so let's focus on this first example. Okay, so what you can see here is the symmetrical arch, okay, with the same level of support. Okay, so this similar level of support at A and B results in the same the symmetrical arch shape. Okay, so and the UDL of 20 kilonewton per meter is applied along the arch span. Okay, so the span is 40 meter. Okay, so 20 meter each side. Okay, so okay, based on this problem, we need to analyze the internal forces of arch at at every 10 meter. Okay, so let's discuss the solution of this example. Okay, and let's go to the next slide. Okay, so based on the procedure of analysis that I have explained in the previous part of lecture. Okay, so you need to find out the support reaction. Okay, and you need to find out the rise y and the angle theta. Okay, at every point. Okay, at a specific point, and by that you can find out the internal forces of radial shear force, axial force, and moment value. Okay, and you can proceed to draw the bending moment and shear force diagram. Okay, so based on this procedure of analysis, let's look on the solution of example 1. Okay, so as a first step, you need to find out directions. Okay, so the normal three equilibrium equations that we have many times applied in previous structures, such as a beam, truss, and a frame, is used. Okay, so and based on this solution, you need to take a moment at A, okay, to solve the vertical reaction at B, and considering another equilibrium equation, which is a summation of force in the vertical equal to 0. So you will solve for the VA. Okay, and considering the summation of force in the horizontal, so you will find that the HA is equal to HB. Okay, but here we still cannot solve for the value of HA and HB, because you need to consider another equilibrium equation, because this arch consists of 4 numbers of fractions. So in other words, it consists of 4 numbers of unknown. So we need to have 4 numbers of equation to solve 4 numbers of unknown. So I have mentioned this in the previous lecture. Okay, so far we have utilized three equilibrium equation. So another equations we need to find out by considering either left hand side or right hand side of hinge, or specifically to refer to point C. Okay, so based on this solution, you can see that left hand side has been chosen. Okay, so the left hand side has been chosen, and by taking a moment at the joint C, we can solve for the HA, okay, which is equal to 400 Newton. Okay, but based on these equations, okay, so you can solve for the HB. So you have same value of horizontal reaction at HB. Okay, so the VA, the VB is a 400 Newton. So since this arch is symmetrical, so it results the similar value of reaction at support. Okay, so and I have mentioned that when you have a hinge in the structure, okay, so and they have a pin support at pin support at point. Okay, so normally you need to consider 4 numbers of equation, and you need to consider one side of hinge, okay, either left or right hand side. Okay, so if you compare these solutions to find out directions, okay, so actually it's similar to the step in the beam with hinge, in the arch with hinge. Okay, so normally this is the procedure to solve for the directions of a structure with hinge. Okay, so let's proceed to determine the internal forces at every 10 meter. Okay, so right here the free body diagram for the arch at 10 meter from support A. Okay, so this is 10 meter from support A. Okay, what you need to do is you need to draw the axial force N, okay, and the radial shear force Q. Okay, so this radial shear force must be perpendicular to the N. Okay, so and you can see that we have an angle here. Okay, and you need to find out the angle here, and the Y. Okay, so the Y, which can be calculated by using the equations that I have explained in the previous part. Okay, so in this slide, if you still remember. Okay, so I have forgotten to mention about the h in the equation in the previous part. So actually the h is a height of the arch, where at the center of the parabolic shape. Okay, let's return to this slide. Okay, so before you can analyze these internal forces of arch, okay, sorry, so this slide. Okay, before you can analyze the internal forces at the 10 meter from support A, so you need to solve for the Y and angle. Okay, so and this Y and angle can be obtained by using the equations of this equation. Okay, so Y equal to 4hx over L square multiplied with L minus x. Okay, so based on this free body diagram, we need to find out the value of Y at x equal to 10 meter. So the L is 40 meter. Okay, the span of arch. Okay, so and the x is 10 meter, and the h here is based on this diagram. The h is 10 meter. Okay, so and simplify this, you can see that y equal to 7.5 meter, and followed by the slope. Okay, so this is equation of slope. Okay, so and substitute all the value of parameter inside this equation. You can see that slope is equal to 0.5 radian, and change into degree. You can see that the theta is equal to 26.57 degree. Okay, once you have all this value of angle and y, you can proceed to find out the internal forces of arch, which is a moment, the axial force, and the radial shear force. Okay, let's really look in detail on the moment. Okay, so by considering this free body diagram and taking a moment at about cut section. Okay, so we have VA. Okay, before you can solve these internal forces of arch, you need to draw this component of each load. Okay, so you need to draw the component of each load. Okay, so for example, here we have two components from each direction, and component from the load. Okay, so which is a 200 kilonewton load, and you can see that this is the 200 kilonewton load here has been changed from the UDL. Okay, so you need to convert the UDL load into equivalent of point load. Okay, so what you can see in the equation, we have a 20 kilonewton per meter. So since we want 10 meter, we analyze the 10 meter internal forces from support A. So you need to multiply this 20 kilonewton per meter UDL with 10 meter. Okay, so it's resulting 200 kilonewton load. Okay, so and find out the component of this 200 kilonewton load. Okay, so by taking moment at the cut section, so we have VA. Okay, so VA multiplied with 10 meter. Okay, so and the HA, okay, multiply with the 7.5, okay, which is a Y, okay, the value of Y that we have determined just now, and UDL load. Okay, so actually this is based on the 20 multiplied by 10 multiplied with the 5. Okay, so which result okay, so which result the 200. Okay, 200. Actually this is 200. Okay, but in the solution here, so it's not in terms of 200, so which is a UDL multiplied by the length. So this is a half of the length of this 10 meter, so which is center of this UDL, or this is the location. Okay, so actually this is a point load that we have converted from UDL, so the location is a 5 meter from the support, meaning that this is the center of this 10 meter length. Okay, so and simplify this, you can see that the moments at this point is equal to 0. Okay, so the moment is 0 at the 10 meter from support A. Okay, and for the axial force here, okay, so you need to consider all the component in this direction of N. Okay, so let's say this is a positive sign. Okay, so this positive directions of N. Okay, so any forces that opposite from this direction will be a negative. Okay, so right here we have a solution for this axial force, where we have an N, okay, positive in this direction, and this 200 sine theta is based on the this component of fraction. Okay, so this component of fraction, this is 200 sine theta is based on this component of load. Okay, so 200. Okay, and we have a negative 400. Okay, so this negative 400 cos theta is based on this horizontal fraction component. Okay, so which is cos theta, and minus with 400 sine theta, which is based on the component of vertical direction. Okay, so this is sine. Okay, so this is cos, and both of them is negative because it's opposite from the positive direction that we have considered. Okay, and this will result the axial force which is equal to 447.21 kN at this point. And for the radial shear force, you need to consider all the forces in this direction. So we have internal forces of a Q here, and the component of from the UDL load, okay, which is will give the cos theta, okay, which is 200 cos theta here, and the component from the vertical direction, which is a 400 okay, so 400 cos theta here, so in opposite direction, so it will give us a negative sign because it's opposite from the Q, and 400 sine theta, which is come from the component of horizontal direction, so in this direction, which is given a sine theta direction. Okay, and simplify this, you can see that the radial shear force at this point is equal to 0. Okay, so let's continue on another at another point. Okay, so this is a point where 10 meter from support B. Okay, so if you realize based on this question, okay, so the every 10 meter will be meet at this finally it will be meet at this center of arch. Okay, so this 10 meter. Okay, and 10 meter if you consider from the left. Okay, same goes for the right hand side. Okay, so the 10 meter is right somewhere here, and another point is at the center of arch. If you find out in the solution, there is no solution for this point, because actually it's not necessary to analyze this point, because this point is a hinge. Okay, so and all the moment, okay, the moment will be 0, but then if for the shear and the axial force is equal to the reaction at support. Okay, so let's look on the another point. Okay, so this is a point where 10 meter from support B. Okay, so and you can see that the y and the angle still remain the same. Okay, with the previous point. Okay, because the arch is symmetrical, So and the point is 10 meter from support, so it will give the same value of y and value of angle. Okay, so and do the same thing as what we have done in a previous point. Okay, so and for by considering by taking moment at this joint at the cut section. Okay, so you can see that we have a VB multiplied by 10. Okay, the vertical direction multiplied by 10, and the HB multiplied with the 7.5 meter, and this from the UDL, and you can see that the moment is equal to 0. And for the axial force, okay, so this positive direction, and in this direction we have 200 sine theta, so parallel with this direction of axial internal axial force, which is positive. And for the these directions, we have the component that opposite from these axial forces, which is give us a negative 400 cos theta. And for this vertical direction component, we have negative 400 sin theta. And the value of axial force for at this point is equal to 447.21 kilonewton. And proceed with the radial shear force. Okay, so this is the direction of positive of radial shear force. Okay, any direction that opposite from this we consider as a negative. Okay, so from here we have Q minus 200 cos theta, which is come from the load, UDL load. Okay, so minus is 400 sin theta. This will come from horizontal, from the component of horizontal direction, and the 400 cos theta, which is come from the component of vertical direction. Okay, so and this will result radial shear force is equal to 0 kilonewton. And you need to bear in mind that the direction of Q and N is opposite from the previous point. Okay, so at the left hand side, the Q is in this direction, okay, downwards, it's like a downwards. Meanwhile, if you consider at the right hand side, the Q must be changed to upwards. Okay, so and the N also must be towards the point, towards the cut section. Okay, so we have done with the example 1, so we will continue the lecture with example 2 later on. So I hope that you stay tuned with me. Okay, see you.